Welcome to the next Calc 3 video. This video is going to cover two main ideas, the directional derivative and the gradient vector. So before we jump into a directional derivative, let's talk about what we've done so far with partial derivatives. So we've calculated partial derivatives to, one, find an instantaneous rate of change, in only two directions though, and finding slope of the tangent line parallel to the x or y axis, and those are our two directions. And so if we take a look at a visual of what we've done so far, in 3 space, we've had some figure, such as this one, where z is a function of x and y. And we've had some point on that figure, and if I put it down on the xy plane, it might fall here, let's say. And so that point is going to have coordinates x naught and y naught. So what we've been able to calculate then is we've been able to calculate the partial of z with respect to x and the partial of z with respect to y. So the partial of z with respect to x would be when we're holding y constant. So that would be a tangent line that comes here. So this is the partial of z with respect to x. So how z is changing as x changes when y is held constant. So we can find the equation of the tangent plane, or we can find the slope in that direction. Now, if we've held x constant, then this direction gives us the partial of z with respect to y. So the question is, what happens if we want to go in a different direction? What happens if we want to find the slope or the rate of change of z moving in this direction instead? How would we do that? What if we don't want to be parallel to the x or y axis and we just have another direction? What are we going to do? Well, you'll see we're going to use this plan. We have some point that is on our surface, and we have some direction u. Okay, so let's jump in. What we're going to do first is we are going to pass a plane through the surface, and that plane is a vertical one that passes through that vector u. So we're going to take a vertical plane that passes through u, and we're going to pass it through our figure. So then, the slope of the tangent line is going to be the rate of change of z in the direction of u. And that's what we're looking for. So what we're going to do next is we are going to choose another point Q that is on the surface and that plane. So we're going to choose another point that's on our surface and is also on that vertical plane. And that point Q is going to have coordinates x, y, and z. So then what we are going to do is we are going to project P and Q onto the xy plane. So remember, we have Q here and we have P from above. So if we project those onto the xy plane then, the projection of P is now going to be x naught, y naught, 0. And the projection of Q is going to be x, y, 0. So now we know that the vector that is created by those projections is going to be parallel to u. So what that tells us is that that vector is a scalar multiple of u because they're parallel, which means it can be written as HA, HB. Okay, and you can start to see the figure here that is explaining what we're doing. So this blue figure S is the figure we're looking at. We have some vector u here. We cut through a parallel plane or a vertical plane rather, that goes through U, and it created this tangent line going through our point. We're choosing another point that is still on that parallel curve and on our plane. Once we project these 2 points down to the xy plane, we end up with a vector that is parallel to U. So that's where we're at so far. So where that leads us then is if we take this vector that we have written, x can now be written as x naught plus ha, and y can be written as y naught plus hb. So what that gives us then is the change in z over h, which is z minus z naught over h. So remember, this is the actual change in z for some unit of measure. So change in z for some unit of measure is going to be f of x naught plus ha, y naught plus hb, subtract f of x naught, y naught, all over h. And that should look pretty familiar. You've seen something like that before. It should remind you of a derivative. So finally, if we take the limit as h approaches 0 to obtain the rate of change of z in the direction of u. And that will lead us to our formal definition on the next page. Okay, formal definition of a directional derivative. So the directional derivative of f at some point in the direction of a unit vector, that's really important, a unit vector. First of all, this is the notation. So this is the directional derivative in the direction of u of some function, is the limit as h approaches 0 of what we wrote on the previous page, if that limit exists. And so, of course, the natural question is, what does this tell us? This tells us the rate of change of z in the direction of u. So before, we could only find the rate of change as x was changing or y was changing as the other variable was held constant. Now that's no longer the case. Now we can go in infinitely many directions, again, assuming you have a unit vector u. So let's take a look at an example of conceptually what this is, and then we'll look at some calculations. Example 1 says, use the weather map in figure 1 to estimate the value of the directional derivative of the temperature function at Reno in the southeasterly direction. Okay, so what we want to look for here, temperature function. So we want to estimate the change in temperature over a change in miles. So if we are going from this point to this point, so we are going the southeasterly direction. Okay, so our temperature ends up at about 60. It starts at about 50. And then we have to estimate that distance. And using the scale here, it looks like that might be about 75 miles. So we get 10 over 75, or 2 over 15. So we're estimating that directional derivative to be about 2 over 15 degrees Fahrenheit per mile. Okay, so what does that mean? That means as we move in the southeasterly direction from Reno, around Reno, the temperature is changing by about 2 degrees Fahrenheit every 15 miles. Okay, so that is the meaning of the directional derivative. Now we need to talk a little bit more about how to actually calculate it. So the natural question is, do we have to use this limit? Of course not. Could we? Yes. Are we going to? No. So that's going to lead us to this theorem, and then we're going to do an example. So the directional derivative of f in the direction of a unit vector, so this is, again, what we're looking for, this directional derivative, is the partial of f at the point times a, and the partial in terms of y at that point times b, and a, b being your unit vector. And of course, it's a similar idea for 3 space. So let's just jump in and take a look at an example. Find the directional derivative in the direction of u at the point 1, negative 2, 0 for this function in the direction of this vector here. Now, first thing I want to point out to us is that this vector is not a unit vector. So in order to use that theorem above, we're going to need a unit vector. So our vector A, the magnitude of A, is the square root of 4 add 1 add 4, which is 3. So our unit vector u is going to be our vector A divided by the magnitude. So that is that 2, 1, negative 2 divided by 3. So our unit vector then is going to be 2/3, 1/3, negative 2/3. Then we also notice we're going to need our partials. So the partial with respect to x is 2xy. Partial with respect to y is x squared subtract z cubed. And the partial with respect to z is negative 3yz squared plus 1. So I forgot about that z. Now we're going to need to evaluate all of those at our point 1, negative 2, 0. So fx at 1, negative 2, 0 gives us negative 4. Fy evaluated at 1, negative 2, 0 is going to give us 1. And the partial with respect to z will also give us 1. So then finally, our directional derivative at the point 1, negative 2, 0 is going to be our partial, negative 4, times the x-coordinate of our unit vector, plus 1 times our unit vector, plus 1 again times our unit vector, which I will tell you ends up being negative 3. Now, again, we need to know what this value means. So this is the change in f over, I'm going to say u, or a. So for every unit traveled, in the direction of our vector A, f of x, y, z decreases by 3 units. And of course, that's only near our point. So we can't just substitute any point at all on the surface into this. That wouldn't work. It's just near this point 1, negative 2, 0. Okay, let's look at another example, and then we're going to move on to the gradient. So here's another example. Find the directional derivative in the direction of u if we have this function, and u is the unit vector given by 2 pi over 3. And then we have to find the directional derivative at the point 1, 0. So first thing, easy, I'm going to start out with the partials. Partial with respect to x is going to be 2x e to the negative y. Partial with respect to y is going to be negative x squared e to the negative y. At this point, we are not substituting in 1, 0. At this point, we are finding the general directional derivative. So we're not substituting in a point. So next thing that we're going to need is we're going to need our unit vector. So we have our angle here. So that's going to be cosine of 2 pi over 3, comma sine of 2 pi over 3. So this is a throwback. Hopefully you can easily recall those values, which is negative 1/2 and root 3 over 2. So then our general directional derivative in the direction of u is going to be 2x e to the negative y times the x-coordinate of that unit vector, add negative x squared e to the negative y times root 3 over 2. So if we simplify that then, we get negative x e to the negative y, subtract root 3 x squared e to the negative y over 2. So now if I want the directional derivative specifically at the point 1, 0, I'm going to get negative 1 e to the 0, subtract root 3, 1 squared e to the 0 over 2, which gives us negative 1 subtract root 3 over 2. And if you're curious, that is approximately negative 1.866. And so again, that is the value of the change in f, or maybe z in this case is how you want to think of it. So the change in z as we move in the direction of u. So for every unit we move in the direction of u, f, or z, is going to decrease by 1.866 units. So that's the directional derivative. Where we go from here is we use that directional derivative in something called the gradient. So that's what we're going to move on to next. Okay, so what we've already talked about is we have the directional derivative is the derivative with respect to x, the partial with respect to x, times a, which is the x coordinate of the unit vector, and we're going to add to that the partial derivative with respect to y multiplied by the y component of the unit vector. So we can re-express that directional derivative. We can re-express that as the dot product of the two partials dotted with that unit vector AB. Another way to write that is, again, those partials dotted with our unit vector u. This part right here, those partials, is called the gradient. So that's what you're going to see in this definition. If f is a function of x and y, then the gradient, which is this symbol right here, the gradient of f is defined as the partial with respect to x, add the partial with respect to y. So a few things that I want you to notice. The gradient is a vector. We end up with a vector. So it's written two different ways, one in IJ notation and one in bracket notation. And of course, it's a similar idea in 3-space. So then, rewriting this, the directional derivative, again, which we have above, the directional derivative is really the gradient of f dotted with u. So as a reminder, this is one way to write the vector. This is the other way to write a vector, bolded versus with vector notation. So let's see how we're going to use this. In example 4, we have some function of 3 variables. First, we're going to find the gradient of f, and then we're going to find the directional derivative. So let's get started. Gradient of f. We have the derivative with respect to x, which is just sine of z rather. Derivative with respect to y, which is xz cosine of yz. And then we're going to have xy cosine of yz. So there is our gradient. Now we're going to use that gradient to find the directional derivative. So if we remember, we have some direction u here, but we need a unit vector. And we're going to notice that the length of u is actually root 6. So we're going to continue by taking u and dividing by the magnitude so that we get a unit vector. So we have 1 over root 6, 2 over root 6, and negative 1 over root 6. So our directional derivative in the direction of u at the point 1, 3, 0 is going to be the dot product of our gradient evaluated at 1, 3, 0 dotted with our unit vector. So to get that gradient, I'm going to go back to the gradient I found and substitute in 1, 3, 0. I already did that for you, and I'm going to tell you you get 0, 0, 3. So then dot with that unit vector. And ultimately, I'm going to tell us that we get the directional derivative in the direction of u at the point 1, 3, 0 to be negative 3 over root 6, which simplifies to negative root 6 over 2. So remember, defining this or interpreting it, this is the change in f as we move in the direction of u at the point 1, 3, 0. Okay, so here is our important theorem. Suppose that f is a differentiable function of 2 or 3 variables. The maximum value, or the maximum slope of the directional derivative, is the length of the gradient vector, and it occurs in the direction of the gradient. The minimum slope is the magnitude of that gradient, but it's the opposite value. We can't find, or we're not going to find, the direction of the minimum slope. Another fun fact, if the gradient of some vector is the 0 vector, so that's the 0 vector, then the directional derivative is 0 in all directions at the point xy. And that should make sense. Directional derivative we would find by taking our gradient and dotting it with the unit vector u. Well, if we have a 0 vector and we're dotting it with any vector, of course, we're going to get 0. So let's take a look at how to use this theorem in example 5. Suppose that the temperature at a point x, y, z in the space is given by that function t, where t is measured in degrees Celsius and x, y, z are measured in meters. In what direction does the temperature increase the fastest at the point 1, 1, negative 2? And what is the maximum rate of increase? Okay, so first thing that we know from that theorem above is that the direction of fastest increase is going to be the gradient. So to find our gradient, we're going to need the partial of t with respect to x, the partial of t with respect to y, and the partial of t with respect to z. So if I go to find that, partial of t with respect to x is going to be negative 160x over 1 plus x squared plus 2y squared plus 3z squared squared. And then I'm going to have negative 320y over 1 add x squared, add 2y squared, add 3z squared squared. And then negative 480z over that quantity squared again. I'm writing this in bracket notation, but of course I could write it in IJ notation as well. So what I'm going to do, just to make this look a little bit kinder, is factor out that denominator. So the gradient of t, I'm going to write as 160 over 1 plus x squared plus 2y squared, add 3z squared, quantity squared, times the vector negative x, negative 2y, and negative 3z. Okay, so now that we have that gradient, we're going to find in which direction the temperature increases fastest. So I'm going to need the gradient at the point 1, 1, negative 2. And that is 160 over 256 multiplied by negative 1, negative 2, and 6. So finally, our direction ends up being 5/8. And then if I use ijk notation times negative I, negative 2j, add 6k. So this is the direction in which the temperature is increasing fastest. So then we are also asked for the maximum rate of increase. And as we saw on that theorem above, the maximum rate of increase is just the length of the gradient. So if we find the length of that gradient above, it's going to be 5/8 times the square root of 1 add 4 add 36, which is 5/8 root 41, which is about 4 degrees Celsius per meter. So every unit we move in the direction of the gradient, the temperature is increasing by about 4 degrees Celsius per meter. 4 degrees Celsius per meter. So that is another use of the gradient. Okay, so let's look at one more use of the gradient and one more example. Next thing that we're going to talk about is tangent planes. So there are two objectives that you can see at the top. You need to know that the gradient at a point is orthogonal to the level set containing that point, and you need to be able to find the equation of the tangent plane and normal line. So we have a figure here and we have some pieces of information here. Let S be a surface that has some equation equal to k. So it's a level surface of some function f of 3 variables. So that's our S here. So if we were to graph f not equal to k, just f of x, y, z, that would be a graph in 4 space. So when we set it equal to some value, we get a level surface, which is this blue figure here. So then what we're going to do is we're going to choose some point P that's on S. And so you can see this point P here that is on that curve S, or on that surface S. And C is going to be a curve, just some curve, that is on S that passes through P. So that's right here. So then any point on C we can denote with a vector. So our vector R that we're going to write parametrically in terms of x, y, and z. So what we're going to do is we're going to let point P correspond to our initial value of t. So we're going to see that right here. This point P denotes some initial value t naught, which would give us some vector. Then, because C lies on S, we can rewrite this level set as f of x of t, y of t, z of t is equal to some value k. So then what we're going to do is we're going to differentiate with respect to t. And so if you think about that, we have f has x, y, z. All of these are defined in terms of t. So we're going to be using our chain rule. So we get the partial of f with respect to x times dx dt. Add the partial of f with respect to y times dy dt. Add the partial of f with respect to z times z dz dt is equal to 0. Okay, so this looks pretty nice. If I take all of these partials, how convenient, that is the gradient of f. And then if I look at what's left, that's r prime of t. Okay, so we have our gradient right now, and then we have r prime of t. Dot product gives us 0, which of course tells us that these two vectors are orthogonal, and we can see that on the figure. So r prime of t is going to be orthogonal to our gradient. So that's pretty cool. Now, at this point, we are interested in point P, of course. So what we're going to be doing is we're going to be substituting in point P here. So what that gives us is that the gradient of f at the point x naught, y naught, z naught dotted with r prime of t naught is equal to 0. Okay, so then formally, what does this tell us? This tells us that the gradient vector at point P is perpendicular or is orthogonal to r prime. Well, r prime is the tangent vector passing through P. So what that ultimately then leads us to is the tangent plane. So you can see that down here. So the tangent plane to a level surface at some point is given by the partial with respect to x at that point times x minus x naught. Add the partial with respect to y at that point times y minus y naught. Same thing with z equal to 0. Alternately, we can write it in terms of the gradient. So this is the same as the gradient at the point x naught, y naught, z naught, dotted with r subtract r naught, and that's equal to 0. Okay, so then you might be asking yourself, well, up here we used r prime, here we're using r, why? So if we think back to writing the equation of a plane, two things you need. You need a point, and then you need a vector perpendicular to that plane. Well, the gradient is perpendicular to the plane, right? It's perpendicular to our tangent vector, so it's going to be perpendicular to our tangent plane, and this is just some point. So r represents any point that's on that plane, r naught is one point that's on that plane. So this or this, both of those are the equation of the tangent plane. The other thing that goes along with it is a normal line. So our normal line is going to pass through that point and is perpendicular to the tangent plane. And this is how it's found. So similar idea to what you did above. Those are symmetric equations. Okay, so I know this has been a long video, but we have one last example to practice this tangent plane and normal line, and then we will be done. Okay, so find the equations of the tangent plane and normal line at that point to that figure. So first thing, just a quick throwback, what does this figure represent? Hopefully we remember that this is an ellipsoid. It's like a 3D ellipse. Okay, so then if we rewrite this in terms of f, we have f of x, y, z is equal to x squared over 4, add y squared, add z squared over 9. And in this case, k is 3, but we, of course, don't really care about that. So then if we find our gradient of f, we're going to get 2x over 4, 2y, and 2z over 9. We, of course, though, want the gradient at the point -2, 1, -3. And so that is -1, 2, and -2/3. So then our tangent plane, we're going to take that gradient and we're going to dot it with x add 2, y minus 1, and z add 3 from our point. And so our tangent plane ends up being negative x plus 2, add 2, y minus 1, subtract 2/3, z plus 3 is equal to 0. Or if we want to put it in standard form, make it a little bit nicer, put x, y, and z on the same side, get rid of that fraction. This can also be expressed as 3x, subtract 6y, add 2z, add 18 equals 0. So that's our equation of the tangent plane. If we want our symmetric equation for the normal line, that would give us x plus 2 over -1 is equal to y minus 1 over 2 is equal to z plus 3 over -2/3. Okay, so last thing we need to talk about real quick is just a special case. And so the question is, what happens if instead of having something that's defined implicitly, we have z as a function of x and y? So what we get then is we can still make this big function f. That big function f is going to be f of x, y, subtract z, right? If we took this, if we move z to the other side, we would get f of x, y, subtract z is equal to 0. So then our gradient in this case becomes f of x of xy, f of y of xy, and then the derivative with respect to z is just -1. So then our equation of the tangent plane becomes f of x naught y naught times x minus x naught plus the derivative with respect to y at x naught y naught times y minus y naught subtract z minus z naught is equal to 0. Now, we're not going to do practice with that because it's pretty similar to the last example. So in this video, we covered directional derivatives and the gradient. Moving on from here, what we're going to do in the last two sections of this unit or this chapter, we're going to be looking at applications. So maximum and minimum. Good luck. Hope everything was clear. If you have any questions, please make sure you ask. See you soon.